All right, why don't we get started? So I apologize ahead of time for my voice. Actually, have a little bit of a cold, or it's either allergies or cold, one of the two. Um, all right, so where we last left off, we talked about. Oh yeah, so the reading. Please make sure you get done with the material, the reading for chapter 3 by the 31st, which is Thursday. And so, it's not that many pages, but please make sure you're keeping up because we're going to be pivoting to threads, and then we're going to have a substantial project involving threads and much of the stuff that we talked about concerning processes. Okay. So where we last left off, we talked about interprocess communication. In particular, we talked about shared memory, and we went through an example with the following C code with the producer-consumer problem. And so, to jog your memory where we left off, we defined the size of that memory in this example to 4096 bytes, and then we made use of the system calls made available by the operating system in order to create our shared memory. And recall, shared memory is, as the name implies, it's memory that multiple processes can use. And so one process allocates the shared memory, and then another process can attach it, as well as the process that creates it. So it's a two-step um, task, as you will. And one, you create the shared memory, and then you attach the shared memory. When you attach the shared memory, you get returned to you, you being the process that did the attach or called the attach API or system call, you get back a pointer, and that pointer points to that region of memory that has been set aside for this purpose. And so in this version of the producer consumer problem, we have the producer, which is going to put information, in this case, a text string, into shared memory. And then the consumer reads out that text string from that shared memory and unlinks it. And the unlink you can think of as freeing that shared memory, returning it back to the operating system to be freely available for anyone who might want to use that memory. Okay. So here we have a bunch of steps. We have the SHM open. That's either to create the shared memory or to indicate to the operating system that you want to attach to it. Right, and so once you do that SHM open, you then do this truncate if you're going to size it. Right, so that's the allocation process. So unlike malloc, which is to allocate memory on the heap, which is specific to that process, when you allocate shared memory, you first signal to the operating system that you want it to set aside memory, and then with this F truncate, that's when you tell it how much memory you need. Now, of course, if these system calls are not successful, if you get an error message, that means for whatever reason, the operating system was not able to allocate it. And certainly that reason could be maybe there's a malfunction, or maybe, bless you, there's not enough memory to go around for this purpose, or perhaps you tried to allocate more shared memory, or a block of shared memory that's larger than the operating system allows any process to allocate. Now, that spec is operating system specific. It can be something that's tuned, but it's usually fairly generous on most most general purpose operating systems like Ubuntu Linux, Mac OS, and Microsoft Windows products. Okay, so then we call the M map, and that's to now attach to the shared memory. What is returned is a pointer to that memory, and you can use that pointer as you would any other pointer. You can, assign to it, you can read from it, and so forth. Okay, any questions about this? No? Okay, so that's the producer side. And in this case, the producer does an sprintf. So it's going to put message 0 and message 1 at that block of memory location that was designated and sized and set aside in the operating system. And again, the shared memory is different from regular memory in that it's so-called pinned, meaning that it exists outside of the running and exiting of a single process. Okay. So this was the consumer that we talked about. And again, the consumer, it signals to the operating system that it's going to use shared memory. In this case, it's going to be only reading, performing read operation on the shared memory. It gets back the file descriptor for that shared memory, so it can now attach to it. It calls mmap to do the attach. and then it goes ahead and prints out or accesses that text string that was put there by the producer. Okay. So then once the consumer is done, it goes ahead and unlinks the shared memory segment. Once that unlink occurs, it's now returned back to the operating system, and in order to allocate it or to use it again, you're going to have to reallocate it. And so either the producer or the consumer can call SHM unlink, okay, because they both have access. So whoever has access to that shared memory segment can actually unlink it, okay? All right. Any questions about this? Does it make sense? All right. And so the project assignment is directly related to this. And in that, you're going to implement a timer. So please think clearly about what timing means. Somebody has to start the timer, right, and record a timer value, and somebody has to stop the timer. And then you're going to make a comparison between the two times between when the timer was started and the timer was stopped. Okay, that's one way to do it. There's no one way to do it. And I look forward to all of your different solutions. Okay, any questions? Make sense? No questions. All right. Okay, so let's continue on. And these slides I've modified earlier this morning because there are some things I thought were important to throw in terms of figures and diagrams. All right. I'll make sure to post them after this. So there are a couple figures that aren't there in the current slides that are on the Blackboard. So let's take a look at communication and so-called client-server systems. Now, a client-server is a type of what's called process architecture. And you have two processes involved, one called the client and one's called the server. And it's the way you think of applications when they're distributed, right? And so these two processes are not on the same machine. And that's typically the model for client server, but it's not incorrect to have them both on the same machine. It's just kind of weird because that defeats the purpose of distribution. And the client process is designated as that process that initiates the communication, right? So if you think about what happens when you fire up your browser and you go to www.amazon.com and you type in a search query and hit enter, right? Well, your browser is a so-called client process. It's initiating a communication with another process called the server process. And in the case of going to Amazon.com, the server process is one of many processes that exist somewhere in Amazon's data center. And the server process is that particular process designated as the entity that receives some message, deciphers it or parses it, and takes some action as a result of what that message contains. And then once it performs some action, that action results in some result, and then it communicates that result back to the client. So the client is the process that initiates the conversation. It sends a message to the server. The server gets that message, does something, and then communicates back to the client what the result is of that communication. Now, if you're interested in more of the details, certainly we have an entire semester in the spring devoted to networking, and you'll learn all of the internals of how the internet stack works more than you probably thought you would know before. So in this class, I'm not going to cover it to the degree that you would in a computer networking course. It's just an important part of operating systems. Okay, so how does this work? Now, the primary unit that you use is an API that exposes a set of methods or routines that allow you to engage in this ability to send data back and forth. And the interesting part about client-server communication, or in a client-server system, is that the two processes don't have to be on the same machine. In fact, they could be somewhere on the same network, or they could be somewhere on different networks across the so-called wide area, right? So you're going to be traversing these communications will traverse multiple networks. And again, I defer to computer networking next semester if you want to know how that all works through your routing infrastructure. But nonetheless, there's an API of the sort called a socket. And a socket contains all of those routines necessary in order to communicate. Now, in a language like C, you have a bunch of different routines that perform all the different functions associated with socket communication. In an object-oriented language like Java, you have socket objects, and the socket object has implementation of methods that accomplish all of those functions needed in order for a process to engage in client-server communication. And so a socket is one of the primary constructs, but it's not the only construct. What predated, uh, no, I'll just go through the list. Remote procedure calls is another, right? And remote procedure calls have been around for quite a long time. And a remote procedure call presents itself to a process as if you had a function, right? And so your process thinks it's calling a function, but underneath the covers, there are services available in the kernel that actually take your parameters to your function, package it up, send it across the wire via a socket, and then waits back for the return value for that function to come across the wire. And so what this remote procedure call does, it makes use of sockets, but it gives the illusion to your process that it's calling a function, right? So it looks just like any function call, but underneath the covers, the mechanism is different. It's actually calling a routine, or if you will, sending a message, and that action being taken is not implemented in a function locally. It's being executed by a server process somewhere on the other side of the network. Okay, and then there's so-called pipes. Pipes are local communication mechanism, right? And we'll talk about that. The name is called pipes because it's the same pipe. If you're familiar with the Unix command line, it's the same pipe you use there. And a pipe is a type of process-to-process communication mechanism. But the caveat with pipes is that it's assumed that there's some relationship excuse me, between the two processes. And typically that relationship is a parent-child relationship. It could also be between two siblings. It's entirely possible to do that. Okay, and then of course there's remote method invocation. That's specifically a Java mechanism for implementing. You can think of it as an implementation of remote procedure calling for Java objects, right? Okay, and RMI, remote method invocation, was developed at Sun Microsystems by Ann Walrath. Okay, all right. Any questions? Okay, so that's what we're going to cover in a nutshell. So, what is a socket? A socket is a software construct, and it serves as the endpoint of a communication, whether you're the entity that initiates the communication, i.e., the client, or the entity that responds to that communication, i.e., the server. And so the socket, it's still called a socket regardless of the the language of implementation, whether it's Java, C, C++, Objective-C, what have you, Python. A socket is still a socket, right? So that's sort of persisted across particular language bindings or language APIs. And so a socket consists, or its identity consists of two major pieces. One is a so-called IP, or Internet Protocol address, right? And this IP address identifies a network card, right? It identifies what's called a network interface, which is effectively your network card. And so every network card on a machine has associated with it a unique IP address. Now, you notice, right, when you go to a website, if you've never tried it, you don't have to use the name of that website in your browser. You could use the IP address directly, right? Your system only cares about IP addresses. That URL, that text name like IBM.com, it's only there for our convenience because it's easy for us as people to remember names of things and not just sets of numbers. So we have this Internet Protocol, or IP address, and that allows this client-server communication system, all the facilities in the runtime for the operating system that implement it. It allows them to identify network cards or network interfaces uniquely. So now what happens? Okay, well, you have a message. It originates on a machine. It goes out the network card, or you have a message that comes into your machine and arrives through the network card. Now, for outbound data, you need to identify which application was the one that originated this message, because you're going to do something different if it's a message from a browser versus if it's a message from, say, Skype or Dropbox or what have you. And so this additional piece of information that identifies our socket endpoint is called the port number. And the purpose of this port number is to uniquely identify, once you're on the machine, which particular application this is either from or this is for. And so there are standard port numbers, and those are typically the port numbers that are numbered from 0 to 1024. And these standard port numbers are set aside and designated for particular purposes. So, for example, port number 80 is for Hypertext Transfer Protocol, or HTTP, or web function. So, if you are a process and you're going to associate with port number 80, you better understand HTTP messages, both in terms of what goes out as well as what comes in, because that's the assumption for those port numbers. So the port number identifies the application, and the IP address identifies the network interface. And more correctly, the port number is part of what's called your transport protocol, right? And I will defer to computer networking next semester because we could easily spend 2 or 3 weeks talking about transport protocols. Okay, any questions about this? Make sense? So if you're going to communicate, you have entity A on one machine and entity B on another machine, and they each have a socket. So you have an IP address and port number for entity A, and you have an IP address and port number for entity B. So in order to maintain a channel of communications with a socket, you need four pieces of information. You need the source port number and source IP address, and you need the destination port number and destination IP address. And those four pieces of information uniquely identify the channel of communication because you need two socket endpoints in order to communicate. Okay, and so a communication, therefore, occurs between a pair of sockets. You don't have, one socket communicating with three machines, not without something special, which is beyond the scope of this class. So at this level, you can assume that communication occurs only between a pair of sockets. Okay, and I talked about the ports below 1024. But there's a special IP address, and that IP address has a particular form, 127.0.0.1, and it's the so-called loopback address. And this loopback address is designated when you want to use a socket, this communication endpoint, where the thing that you're trying to reach or send messages to is on the same machine, right? And something special happens when it's on the same machine. Why, block for I/O, wait for the network card? It uses shared memory as an optimization, right? Because it's never going to leave the machine. So why use all of this machinery that's needed, particularly when that message needs to leave the machine? So this special IP address called the loopback address is intended when you want to communicate to a machine to another process rather that's on the same machine. Okay. Any questions about this? Make sense? Yeah. Okay. So let's take a look at an example. So we have two hosts. Let's say we have a host as the name of a machine that's connected to the internet, and machines have operating systems, and operating systems run processes. And so we have two hosts, host X, and that might be your laptop or cell phone or what have you. And then we have a web server somewhere. Maybe that's running in a data center at Amazon or Netflix or what have you. So host X has a socket that has been created, and it, as a communicating endpoint, as we said earlier, has an IP address and a port number associated with it. So it has IP address 146.86.5.20, and its port number 1625. Now, again, I said earlier that well-defined port numbers are designated for particular purposes, and port 80 is for HTTP traffic, right? And so you'll notice here for this web server, the port number is 80, so we have this colon 80, connoting the port number. And then for the web server, its IP address is 161.25.19.8. And so these two sockets define the particular channel of communication, this edge in the diagram drawn between host X and the web server. Any questions about this? Make sense? Yeah. Okay. So let's take a look at the two types of sockets that you can have. Well, it's really three, right? But we're more so going to focus just on the two major ones because the third one is not always configured on a network by a network administrator. And I'll comment on why that is the case. And so we have a so-called connection-oriented socket. And something called Transmission Control Protocol, or TCP, implements connection-oriented client-server communication, or sockets. And it's called connection-oriented because it's reliable. right? Everything that you send, you as the sender, TCP guarantees that it will be delivered in the order that you send it. So if you send a message to, let's say, a banking application, and it says deposit $100 and then withdraw $20, it's going to happen in that order in which you sent it, right? And TCP guarantees so-called in-order delivery. It also, if there's a break in communication on the channel between the two communicating endpoints, TCP detects that and it resends on your behalf. So with TCP, you as a sender, all you do is you use your socket interface and say, send this, and TCP takes care of all those details of retrying and validating that it was in fact delivered at the other endpoint in your communication. It's pretty neat, but all of that comes at a cost, right? And that's one thing you'll learn throughout the rest of your education is that every feature comes with a cost. Now, the cost of that is slowed communication because all of that checking and the resending and validation takes time. And that means that the amount of data that you can send via TCP, yes, while it's reliable, it's connection oriented, you're not going to be able to send as much data had you not done all that, you being TCP, not done all that validation and error checking and in order delivery guarantee. The other type of socket is so-called connectionless socket or UDP, unreliable datagram protocol. And UDP doesn't have any of those guarantees. So if you as a sender use UDP in your socket, it'll deliver that data really, really fast, but there are absolutely no guarantees. So what does that mean? If you sent two messages in a banking application and that message was being sent, those two messages were being sent by UDP, you could send the first message, deposit $100, and the second message, withdraw $20, and the first message might not even get there. Or the second message might arrive before the first message, right? There's absolutely no guarantee, but it'll happen quickly. So you might ask the question, then why have one versus the other? It all depends on your application. So when you design your distributed applications, these processes that are scattered across the network that communicate with one another to achieve some purpose, you have to think really hard about what it is your application is going to accomplish. And one of the considerations from an engineering standpoint is, can your data or can your system afford to lose data? Now, for something like a banking application, no, you can't afford to lose messages or messages to be dropped or arrive out of order or be corrupted. You can't afford to do that because that means if you were intending to first deposit $100 and withdraw 20, what happens if the balance isn't enough if the withdraw 20 comes in first, right? Uh, Whereas connectionless, all right, it's fast. Take an application like audio streaming. Now, if audio streaming drops a little bit of data, you might not even notice that a little bit of audio data was dropped, right? Or something arrived out of order. Or maybe there's a little hiccup. What do? You just rewind the stream and you just keep going. It's not catastrophic if you lose data for something like audio streaming or video streaming, right? And so when you design your application, if you're designing a distributed application and it comes time to look at how you communicate, you have to really think about whether this in-order delivery and these guarantees afforded by TCP are important, or if you just want raw speed and can tolerate lost, out of order, and or corrupted data. Okay? All right. Any questions about this? Make sense? Okay. And so the third type of socket is called multicast. And what multicast means is that you, the sender, you send one message, but that message gets delivered to more than one destination process. And so how that happens underneath the covers is that each process that wants to receive that communication joins what's called a multicast group, right? And underneath the covers, the route infrastructure or the network infrastructure creates what's called a multicast tree, and all of the nodes that are interested in receiving that communication join this group. And whenever you send to the multicast group, and all of a sudden, that message is propagated to everyone who expressed interest in receiving it. Now, the danger of that is you can imagine over the wide area, multicast, meaning across networks. The multicast can be a very nice mechanism for doing denial of service attacks and flood attacks. You sort of send so much traffic to somebody on a network that they can't engage in legitimate communication. So a lot of administrators will turn off multicast forwarding, meaning that if a multicast packet comes onto my network, I'm not going to forward it. I'm not going to allow it onto my network. So you're not guaranteed that multicast will work over the wide area because administrators typically don't like multicast. Now, will that change with IP version 6, the new growing network protocol? It may change, and I'm certain it will the next couple of years, especially as 5G comes online. Okay. Any questions about this? Make sense? All right. So in the book, there's an example client-server application, and it's called the date server. And this date server just gives you the day and the time, right? The date. And so you have two processes. The server process responds. It goes ahead and gets the local time and date and sends it back to the client process, which just simply connects to it. So in the code, this is the date server, and I'll just sort of walk through it and we'll try this out. Okay, I'll try it out on my machine. And it's because it's Java, and this is the example in the book, we don't have to do it in Ubuntu. You can do it on whatever platform has your Java virtual machine. Could be Windows, Linux, what have you, Mac OS. So we start out, and you'll notice here, because this is Java, Java is object-oriented, and Java traffics in user-defined types called classes if you've never had Java. And the entry point for every Java program, just like in C, is the main function. Now, of course, because it's an object, it's the main method. And this main method, you'll notice, is static. That means it pre-exists the creation of that class. And so this main method, any static method in Java, you can call it without having to instantiate that class, right? So here we have our main, and our main has a string array args, and that's kind of like Java's version of saying argc and char star star argv. They just have a single array because the array has a length property associated with it. So you don't need a separate count. So what happens? So we create this server socket here. And when you create the server socket, you give it the port number that you want to associate with this particular process, this date server. And so the server socket, its purpose is to listen for incoming connection requests, right? That listening for incoming connection requests is done inside of a tight while loop, and you'll notice it's an infinite loop while true. Now, in an actual commercial implementation of a server, you're not going to say while true, right? You're going to say while the shutdown condition has not been issued, right? Because you want to be able to have this thing exit gracefully and close databases and purge memory and pull down all of the interprocess communication resources and so forth. But nonetheless, in this example, it's just talking about the interaction between the server and the client as it pertains to the socket interface. So you create a server socket, you enter a tight while loop, and in this while loop, it just keeps waiting for incoming requests. Bless you. And so this waiting for incoming requests is done via the accept method on this server socket. And so this accept method, it's a blocking call. And this blocking call says, okay, well, the process is going to pause. It's going to wait until it's signaled ultimately by the I/O controller associated with the network card that there's incoming data available. So when this accept blocking method on the server socket returns, it returns back a single socket called a connection socket. And it's that connection socket that acts like the conduit, if you will, between this communicating server and the client on the other end, the client process on the other end that contacted it. So we create the server socket, the ability to wait for incoming requests. We actually wait for an incoming request. When the incoming request arrives, it returns, the accept returns, it's a blocking call, and then we get a client socket, a connection socket. In this particular example, the connection socket is accessed by a reference called client. And now through that client connection socket, through client, the variable called client, we can now interact, this being the server, you can interact with the client. So in this particular case, they're being very, very simple, and this is not how a typical server would be. but it's an absolute valid server from a theoretical standpoint. Now, this server, it's important to note, does not receive any incoming message from the client, right? But you could absolutely do that, and maybe we'll do that maybe another 2 weeks or so in an application. But nonetheless, the first thing that this server does, it accepts the incoming request for connection to communicate from the client, and then it gets its output stream. Now, this output stream, that's a Java thing. And an output stream you can think of as a channel or conduit which you can send data, right? The analog to that is called an input stream. That's a conduit or channel through which you can receive data. So it's called a stream because a stream is a sequence of bytes, one byte after the next byte after the next byte. So if you want the server to be able to send data to the client, you have to get the output stream from the connection socket that allows you to reach the client. Conversely, if you want the server to be able to receive information from the client, you would get what's called the input stream from the connection socket that allows you access to the client on the other end of the communicating endpoints. Does that make sense? Any questions about this? Okay, so these are specifically Java-isms. They're not C constructs. So now what does our server do? It says, okay, well, I'm going to take my output stream, P out, right, that allows me to communicate indirectly through the connection socket to the client, and I'm going to print on that output stream the text of the current date. So the server gets the date, converts it to a string, and uses that string as a parameter to the print going through that output stream indirectly through that connection socket to the client. Okay? All right. Any questions? No? All right. So what happens then after that? Okay. Well, it goes ahead, it being the server, and it closes that connection to the client, that socket, and then it comes back in the while loop again, iterates again, and waits for another incoming request. So, you can have one client attached, and then another one, and then another one, and then another one, and another one. And when we talk about threads, we'll see a more sophisticated way of doing this, but we'll wait until more material pertaining to chapter 4 before we talk about threading. Okay, so let's take a look at the client side. And the client is going to initiate contact. It's not going to physically, in this case, it doesn't physically send a message, but it could, right? So the client creates a socket. It has its main method, static void main, string array args. It creates a socket and it uses the loopback address, and it's going to use loopback in this case because the client and the server are assumed to be, in this example, on the same machine. Now, if they were on different, on different machines, you would have the IP address for that other machine in order to communicate. All right. So what happens then? So the client creates a socket, and you notice here there's no server socket here. It's a client, not a server. So it creates a socket and gets back a socket object reference, and that's now a channel of communication to the entity on the other side for the communicating endpoint, i.e. the server. And if there's a mistake or an error or it can't connect, you're going to get some exceptional condition. It's an error condition. But if it does not have an error, then the client says, okay, I want to be able to receive information from the server, right? So you get this so-called buffered, this input stream reader. And this input stream reader allows you to get information that's being sent to you. So the first thing that happens is that the client, after creating the socket, it gets the input stream from that socket. So indirectly through that channel of communication, that socket interface, it's saying, I want to be able to read from you information that was sent back by the server. So it gets the input stream, and then it wraps that input stream into an input stream reader, the ability to read from it, and then it creates a buffered reader from that. Now, a buffered reader just provides memory in which to store things that you read. Because if you're reading, say, 1024 bytes off the network, you need to store it somewhere. So you're going to wrap that reader in a buffered reader, in a buffer. It's called a buffered reader. Okay. Any questions about this? Make sense? So we'll actually try this. So the buffered reader, then, it goes ahead and it tries to read a line of text in a while loop, and each time prints out what was read. Now, of course, what is read is the text of the current date and time sent by the server. So it prints that out, until it gets null, meaning that there's no more input. After that, it closes the socket and then exits. Okay. Any questions? Make sense? All right, so let's try this out real quick at the command line, and we'll see it working in action. And in this particular case, the client process does not send anything. If it wanted to send something, you'd use the output stream, and then you'd print to that output stream, right, in order to send something from the client to the server. But this one doesn't send any message. It just connects with it and reads something that's sent by the server. Okay. So let's exit this, and I'm going to keep this up so that I can know what I'm going to type. All right, so we had the server, date server, and I already have Java installed, Java-version, yep, J2SE version 13. All right, so vi date server.java. Okay, so we're going to import or bring in all the libraries for the package in Java that has all the network communication. So import java.net star, all the libraries. Now, if I were to do this for real in a commercial application, I wouldn't import star. I would import the classes that I need individually, because when you import star, that makes your image, the size of your process, much larger than it needs to be, right? Only bring in libraries for classes that you're actually going to use. Okay, import java.io.star. All right, and so public class date server, open close curly brace. Let me come up here, public static void main string args. Let me open close curly brace here. And it's really important practice. I like to close my blocks when I first define them, so you don't get those really hairy cascading errors because you didn't close the block. All right, so we have the main method. So we're going to do the try catch block. Try catch, that's how you do error handling. Catch, and it's IO exception, IOE, open close curly brace. Bless you. Okay, so we have our try catch block, and let's just fill in the try right now. Okay, so we say server socket, sock gets new server socket, and we have port 6013. Okay, so next we're going to say while true. I'll leave out the comments in the interest of time. While true. I thought I had a question. All right. So we have our while block, our iteration block. So let me do this. Set AISM. There you go. So we say socket client. So the connection socket is the result of accepting on the server socket. So sock.accept. So we create the connection socket, print writer p out gets new, print writer client gets the output stream. Okay, true. And then we're going to do the print line, p out, print line. The text for the date, new. So we instantiate a date object, java.util date. And then we call to string. This is called an anonymous class. All right. So we have the anonymous class for date, convert to string, and then we close client. We close the connection socket. Close. There we go. All right. So I have to make sure to fill in the exception handling for the IO exception. System error print line IOE. So that's printing out to standard error, which is immediate printing, the Java way of doing it. Okay, so that looks like our class. All right, there we go. So let's now work on Any questions about this? All right, let's work on the client. Write and quit. So let me bring this up to so I know what I'm writing. Date client.java. Okay, import java.net.star, import java.io.star. Okay, public class date client, open close curly brace, public, I'll write the main method static, void main, string args, open close curly, right, set AISM, okay, oops, there we go. Uh, all right, try catch block, open close paren. So we're going to catch the IO exception, IO exception, IOE. So inside the try block, socket, sock, new socket. So the client creates the socket 127.0.0.1. So the loopback address, port number 6013. Okay. So now input stream in is sock get input stream. So the client gets the input stream to be able to receive data from the server. So we buffer it, buffered reader, oops, reader, buffered input, new, buffered reader, and we wrap a buffered reader around the input stream reader, new input stream reader, gets the input stream, and we close that. And so now let's get the actual data. Okay, string line. Okay, that's going to hold a line of text while line gets input stream read line. So we're going to retrieve the text. All right, and then if the line read is not equal to null, it's not a null reference. All right, so I'm going to do an open close curly because I like open close curlies. We're going to system.out print line, the line that was just retrieved through the buffered reader indirectly through the socket the client made with the server. Okay, so now we're going to close the socket, but we don't want to do that inside the while loop. We want to do it outside the while loop. So we're going to say sock close. Okay, that looks good. So now we're going to look at the IO exception, put in the handler system error, print to the standard error, print line, whatever that was, IOE. Okay, all right. So hopefully, any questions about this? All right. Hopefully, I don't have any typos. I'm sure the compiler will tell me, and we'll test this out. I forgot the semicolon. Did I close that statement? Yes, I did. Okay. Okay, so let's compile it. Java C -d dot star dot Java. Buffered. Oh, need two R's. So date client, vi date client line 12, Java. So we go to line 12 and buff, two F's, buffered. I think that's it. Let's find out. Java C. There we go. All right. Awesome. All right. So now let's run the server, and then we'll run the client and see what happens. So Java dash class path dot date server. Oops, forgot the dash. There we go. Dash. Dash CP says the class path or the location where you find class files is in the following directory, which is the current one. So we run the date server. And it's interesting if you choose a career writing servers, so-called backend, right? The backend are the algorithmic non-graphical parts in the front end. Is typically the user interface and the graphical parts. It's not exciting when you see a server running because it just sits there and waits for requests. Maybe you can print out, print line or something when the server is running to let you know what it's doing. But it's not as interesting as when have user interface and graphics swirling on the screen and buttons doing stuff. So certainly if you choose a career in software development, and you choose, whether you choose back end or front end, you kind of have to make a choice if you're going to deal with the user interface type parts, or if you can deal with the back end stuff. But back end is always less visually pleasing when you are running your programs. All right, so let's run the client, Java-CP client. So we run the client. Oops, what just happened? Oh, forgot. CP dot current directory client. There we go. Good luck. Oh, if I can spell that correctly. So let me try one more time. Clear. Client with one C. Okay. Could not find client. Oh, date client. All right. Uh, date client. There we go. So there it is. So it ran, ran, it ran. So, it's a fairly simple one. And you'll notice that the time is actually changing. It was, let me clear this. Clear, right? Oops. We have 10, 17, 55 seconds. We have 10, 18, right? So the date is actually, changing. So it really is running. Now I could certainly put some print statements in the date server to let you know that it's actually, doing something. But I just want to show you the actual example that's in the book. And so when you see the examples in the book, uh, do try them out, right? They're intended to give you some exposure to what the system call interface really looks like. Now, for the operating system bits, they use C for this textbook, but for this communications client server example, they use Java because Java is a very easy language to use for implementation of network applications, distributed systems. Okay. Any questions about this? Make sense? Yeah. Okay. All right. So let's move on. All right. So we just saw an actual example of a date client and a date server, and this gives you the flavor, as it were, of what it is to write a client server application. Albeit it's a very simple one, and if you've taken computer networking, this would be very basic to you. So the one thing that I would add to this, and I really wish the book did that, but I just want to mirror the book here, is that a client typically sends a message to the server, not just connect and receive and retrieve some piece of information, but it is showing you that a socket does do what we have described. Okay. So are there any last questions about this? No? Okay, so let's move on to the next topic. Remote procedure calls. Now, the remote procedure call is a client-server application, but it's presented to the client as if it's just calling a function. So you have a function in your program, and you just call it. And some functions, most functions are like regular functions. It's a local function call. But with these remote procedure calls, they're special functions, and they look just like regular plain old functions, except when you call these special functions, it actually takes the parameters of your function, it wraps it up, and sends it out across the network to some server. And that server implements what it was that function is supposed to do. And that's called a remote procedure call because the execution of that function or procedure is happening on a server somewhere in another process. And so this RPC call needs a bunch of infrastructure that is provided by the kernel, all right, and some other pieces called the Matchmaker. And so RPC abstracts procedure calls between processes on different machines across the network, right? And so it makes it look like a regular function call, but it's not. And as a client-server implementation or client-server system, again, it uses the socket interface underneath the covers. Now, when I say it uses, you, the program that calls that procedure, you don't have to do anything with sockets, anything with client-server programming. You just call that function, right? And the system provides all of the machinery to do that packaging and that call with the sockets. And so you're going to need your IP addresses underneath the covers, and you're also going to need port numbers to know which process should get this message, right? Okay, and so you have an important piece of machinery called a stub, right? And on the server side, it's called a skeleton, right? Now, a stub is a proxy. A proxy is something that does an action on your behalf. So it's the stub's responsibility to present to the process on the client side to present to it an API call that looks just like the function you're trying to call, right? So it presents a function that's callable by processes locally on one machine, and then it also handles the interaction between the socket on one machine and the socket on another machine, right? The client socket and the server socket. So functionally, we have this following type of diagram. On this, the big box here represents a machine, and the machine on the left is going to be your client, right? And the machine on your right is going to serve as your server process. Now, again, the client in step one, it just calls a function, but that function looks like any other function, but instead of calling as it usually would call, right? It calls into the stub. Now, that function, when you call it, that execution goes into the client stub, and that's in the user address space, right? It's a user level process, and it integrates with the kernel services. And so what does that stub do? Okay, you call the function. That function's implementation is in the client stub. The client stub takes the parameters of that function, instantiates a socket call, and then sends that data with your two pieces of information, the parameters you specified, and the name of the function, right? So the name of the function and the parameters that you called it with are sent across in a socket. So that client stub then takes all of that payload information from the function call and instantiates a socket and then calls that socket and sends that data across. So waiting on the other side is a process that listens for the incoming communication. This is called the matchmaker. And the matchmaker says, okay, well, you're trying to call function number one, or function number two, or function number three. Now, I have knowledge, I being the runtime on the other side, the skeleton. Well, here it's called a stub, but in practice it's called a skeleton. So on the server side, that skeleton or server side stub says, okay, here's a piece of information that is the set of parameters that were called, that were sent in the function call, all right, specified in the function call, and here's the name of the function. Now, given the name of this function, I have a mapping that associates every server process with a function name, and I know what port they're associated with. So if I see function number one, I'm going to look in my table. That's associated with port 6000. I'm going to return back that port number so that then the stub on the other side knows which port to use when it connects via its socket. So there's a two-step process. The first step is that the stub collects the parameters for the function and it knows the function name. It then requests from the other side, it's message number three, here's the function name, what port number should I use for the socket? It sends back that port number that should be used. It then contacts directly that process, indirectly through that server skeleton or server-side stub, that particular process because it is associated with the port and it knows that port number, right? So any questions about that forward direction? Make sense? Okay. So now you call that function, it's a process, right? And that process gets that data across the wire from a socket, right? It does some command or does some action. It then gets the return value, right? And because it knows who the source was, the source IP address and source port number. It knows to whom it should return that return value from the function, but instead of returning from a function, it's going to send it through a socket, through that same socket from which it got that information. So that's edge number 6. And then this server stub then forwards that information through the socket. Now, there's an important piece of information that I did not mention, and that's called marshaling. When you're going to take something from an address space and send it across the network, you have to so-called serialize it. You have to put it in a form where it's sequential, right? So if you have a block of memory, you have to read out the first byte, the second byte, the third byte, the fourth byte in some order and send it across the wire. And on the recipient side, somebody has to take this first byte, second byte, third byte, and so forth, and reconstruct that block of memory on the receiver side. So the encoding from a data structure to a serialized format on the client side is called marshaling, and the decoding of that serialized format to reconstruct the data structure rather, in memory of the recipient is called unmarshaling. And so this marshaling and unmarshaling is performed by the client stub and the server stub or server skeleton, right? So the marshaling is conversion from a data structure to a stream-based or serialized format. The unmarshaling is a dual operation, conversion from a serialized format to the data structure in memory. Complicating this is the fact that two machines can be entirely different operating systems, can be entirely different architectures. And by architecture, I mean things like endianness, right? Endianness talks about how you represent bytes. So if you have a 16-byte number, right, you have the uppermost 8 bits, and rather a 16-bit number, you have the uppermost 8 bits and the lower 8 bits. Now, of course, some platforms, when they represent it as a stream, they send the uppermost byte first and the lower byte second, right? Others send the lower byte first and the upper byte second. So if you're dealing with two platforms, and let's say you have platform A and platform B, and you have 16-bit number, so it's byte 0, this is byte 15, and you chop it up into the upper and lower, right? Platform A might represent it as the upper first and lower first, and platform B might represent it as the lower first and then the upper first. So if you're going to transmit this 16-bit number across the wire, you need a common representation that all your endpoints understand, right? And so that common representation is typically, it takes form as a special data language. And so part of the job of the client stub is to translate from the representation of process A to this common format for the wire, this marshaled format. And then part of the responsibility of the server stub, or skeleton as it's called sometimes, is to do the dual operation to translate from this wire format to the format in memory on the server process. Okay. Any questions about this? Does that make sense? Now, for the most part, remote procedure calling, are there people still using it? Not that many, but there are still a lot of people using remote method invocation, which is the RPC mechanism for Java. So you will encounter it if you write Java applications, not so much so if you use other languages. So, well, people still do RPC. Web service has taken over from RPC. Okay, all right. Any questions? Make sense? Okay. So we have these proxies. On the client side, it's a stub. On the server side, it's also a stub. It's named a skeleton. And they're responsible on the client side and server side for marshaling on the client and unmarshaling on the server. The server side stub receives its message and it unpacks this from the serialized or stream-based format to that data structure in memory that has to be built up. And so in Windows, that language that you use to define data when it's being transmitted on the wire is Microsoft Interface Definition Language. In other operating systems, it's called the External Data Representation or Interface Definition Language. Okay? All right. So this data representation is a format that you use to account for these two different ways of representing data. One is called big endian and one is called little endian, which I described before. And it just says when you're describing numbers, which byte do you represent first, the uppermost byte or the lowermost byte? And that's the same for the 64-bit quantity or 32-bit quantity or 16-bit quantity. Okay. So another issue with remote procedure calls is that you can have failures underneath the covers. So when you send a message, sometimes that message gets lost, or sometimes that message takes too long. And when that happens, in order to guarantee that messages are delivered, sometimes you have to resend it. And that's handled by the underlying TCP runtime. But remote procedure calling is a little bit different from a socket because on the client side, it just looks like a local procedure call. And so it's the stub and it's the socket that handles all of this sending, resending. But the problem is if you resend, underneath the covers, it looks like you're calling a function to the client, but that has to result in that function call's action only happening one time, right? So you need to guarantee what's called at most once semantics, which in the literature is called idempotent, IDEMPOTENT, right? That means you have to preserve this singular execution semantic. So regardless of how many times something is resent, if process A calls its local procedure once, it can only happen on the server once, right? So let's say if you have some function foo, and you call foo, and you give it a parameter p1, right? To process A, it looks like calling foo, but underneath the covers, you have your stub, right? You have your socket, and then you have all that unmarshaling happening on the other endpoint, right? And so, like any function call, if you call a function once, you only expect it to happen once. But it's a little bit different, and there's more doing that happens because you have a separate process on the other endpoint underneath the covers on the other endpoint for the socket, on the other socket. Okay? All right. Any questions about this? Make sense? Okay. So let's take a look. Well, you have this idempotency, this at most once semantics with a call for the local procedure that has remote execution. And the operating system acts as this matchmaker, which implements this rendezvous communication, meaning both processes have to be active in order to physically do the send and receive. So this is in the book, and this schematic is a little bit busy, but it describes a series of steps between the sender and receiver endpoint, i.e. the client and the server process, as it pertains to the actions of the matchmaker. So here we have on the client on the left-hand side, and it goes from top to bottom, left to right. On the left-hand side, you have the client. On the right-hand side, you have the server. And then this annotated circle in the middle is a high-level view of the message content. The edge direction for the arrow connotes the direction of communication. So if you go from left to right for the arrow, that means you're communicating from client to server. From right to left, your right to your left, that means you're communicating from the server back to the client. So we start out up above, and the client calls that remote procedure, and underneath the covers, it calls into the kernel to send a particular remote procedure call to procedure X. And so X is the name of the function. It doesn't matter if it's a text name or if it's like an identifier like function number 1, function number 2. So the kernel then contacts the matchmaker on the server side. And so that information payload has who it's from. It knows the IP address. It knows the server address it's trying to contact. But the port number, all it knows is who the matchmaker is. It doesn't know what the server process port is on the recipient side. And so the content of the message is, hey, can you get me the port associated with the process that's going to execute the behavior of this function number X that I'm trying to call? So then the matchmaker on the server side gets this message. consults its table, and it says, all right, for function number X, what's the port number? It gets that port number P. So then it replies back with a message that says, okay, well, I'm the matchmaker on the server. The port number that you for function X is port number P. So it sends that back to the kernel on the client side. So the kernel says, okay, great. Now I know the port number. Let me fill that in, and now I can make a regular socket call. So the kernel then replaces the port number and sends that packet, if you will, that unit of information to the server side. And it has the clients is from, servers to. Now it knows the actual port number, and this is the actual contents of that message. So the server gets it, performs some action, gets back a response, sends back the reply through the socket, gets delivered as the return value to the calling client program above. Okay. Any questions about this? So essentially, the matchmaker is the thing that knows which port number is associated with which server, and you can have literally a different server process perform the actions associated with each of those functions. And to the calling client, it has no idea, it has no idea that this function involves execution across the network. It just looks like you called a local function. Okay? All right. Any questions about this? Now, this is a kind of controversial topic because when I worked at Sun Microsystems, I actually worked on a team that did a bunch of work with RMI on a distributed system called the Genie technology. It's available through Apache, now called Apache River. But nonetheless, the idea that you hide the details of the underlying network, is kind of flawed, right? Because when you have a failure condition, functions usually just execute. But from a programmatic standpoint, what happens if for some reason this function doesn't complete because something happened with the server process? So at that point, your calling process A has no idea what to do because this function failed. And so one of the arguments, and originally RPC, which was intended to hide the details of the network from the calling process, that a local function looks just like a server call. It's hidden from you. So there's a famous paper, and I can post it on the Blackboard. It's an easy read, called A Note on Distributed Computing, which argued that you should not hide the details of the network because that failure condition, process A has no way to respond to it. Do I call a different function? Do I shut down? What do I do? So how do you respond if you don't know what happened? And so that introduced the idea that you should make visible to the calling client all of those details associated with network failure. Okay? All right. So it's sort of a controversial thing, at least it was back when it originally came out. Okay, so that's RPC. Let me do a time check. So the next client-server communication mechanism is called pipes. And a pipe is kind of like a socket, but a pipe is only for communication between related processes on the same machine. And so a pipe, one of the very blaring examples of a pipe is something that every Unix command line has, right? And I'll talk about that in a second. And so a pipe allows you to communicate between two processes. And one of the concerns that you have is whether that channel of communication between two processes is unidirectional. So messages can only go in one direction. Or if it's bidirectional, you can have messages in two directions. And if it's bidirectional communication, is it full duplex or half duplex? Full duplex means that you can communicate in both directions at the same time. Half duplex is you can communicate in either direction, but only one direction at a single time, right? And then for these pipes, there has to be a relationship, either parent-child, child-to-parent, or between two siblings, meaning that they have the same parent. And so one of the questions someone had asked through the development of operating systems is, can you use pipes over a network, right? Well, theoretically you could, but just use sockets so you can make public all of those failure conditions associated with the network. And so a pipe in Unix is what you see when you put commands together, right? So the cat command says list out the contents of a file, right? So here's the Java file, and I'm going to say cat date server.java. And what does that do? You see all the contents of that text file go whooshing across the screen. Now, one of the things I can run is this word count command, WC, and WC, it'll count all the words in a piece of text. And if I say WC space -L, it'll tell me the number of lines in that text, all the new line characters. So I might want to say cat date server, but take the output of that and make it the input of that word count. So if I said cat date server.java, okay, that outputs something. But let me take that and input it through this thing called a pipe. That's vertical bar, right? And I'm going to input it to WC, and WC is going to tell me the number of lines if I say -L, right? That's a prime example of a pipe. So in this case, the command line interface is a process. It's running two children. The first child it runs is date server. The second child it runs is WC. Now, the output of the first child, date server, is going to be sent through a pipe. That's what vertical bar means. And that's going to be sent to the input of the second child, which is WC-L. Okay? So if I do this, I get 25. It's 25 lines, right? So that's a prime example of a pipe. It's not just something for Unix commands. It's literally something that you can program yourself, right? And there has to be some familial relationship, parent, child, or siblings, in order to use pipes. So pipes have to be between related processes, whereas for sockets, those processes don't even have to be related. They don't even have to be on the same machine, okay? So that's what a pipe is. There has to be some relationship and allows you to communicate between related processes. There are different types of pipes. There are ordinary pipes, which is what I showed you, and there are named pipes. Ordinary pipes must exist between the parent-child relationship, but named pipes have a name associated with them, and these pipes exist outside of the process. So with ordinary pipes, once the process ends, the pipe is gone. With named pipes, that's managed by the operating system kernel, and the processes don't have to be attached at the same time. Okay, you don't have to have this parent-child relationship. You can be any process on the same machine and use a named pipe. Okay, all right. Any questions about this? Make sense? Okay, so this is what a pipe looks like. A pipe has is on Unix implemented as a file descriptor, and so for ordinary pipes, you can implement a producer-consumer type setup. So the producer is going to write to the pipe, and the consumer is going to read from the pipe. Now, of course, ordinary pipes are usually unidirectional, so you're going to need two pipes if you want to communicate bidirectionally. You're going to need one to have communication from the parent to the child, and one from the child back to the parent. So in that case, it looks like the following. You have a file descriptor. You have an array of two file descriptors. They're integers. And you have one, the file descriptor 0 is the one for reading. File descriptor 1, the standard is the one for writing. So here you'll see the first file descriptor in position 0. The data is going to come into the parent, and the next one, the second one in that array, is going to be for outputting data. And likewise for the child. So if we take a look I'm not going to talk about that slide. The important part is this is an example of a pipe. In this particular example, and let me check the time. Yeah, we have 1 minute left. I'm not going to force this. Why don't we end here? No, we're 10:40, 9:30 to 10:45. Yeah, 10:44. Okay, let's end here, and I'll just briefly pick up with this on Thursday rather than rush through it. Okay, so I will see you all on Thursday, and we'll pick up for like 5 minutes on pipes and go forward with threads. Okay, all right. Look forward to your submissions tonight. Please make sure it runs before you submit it, and zip only. No RAR, no 7-zip, none of that. Just zip only. Okay, all right. I will see you all on Thursday, and that's time.